This is the second of two videos on the reactions of alkynes. We've already looked at the unique reaction, alkylation, of terminal alkynes, the two-step reaction where we take a strong base and rip the proton off of a terminal alkyne, and in the second reaction, react that with a primary or methyl halide to get a alkylation product, the alkylation of a terminal alkyne. So that was the unique reaction of alkynes, that's typically not seen for alkenes. So now we're going to look at the reactions that are like the alkenes, where the pi electrons are attacking electrophilic sites, whether it be the bromine in Br2, an acid catalyst proton in aqueous solution, or just pure acid hydrogen chloride with an alkyne. Some of the reactions that we get that are very, very similar to what we saw with alkenes, just one little change, one little difference. The alkynes are typically less reactive with these electrophiles in polar reactions because of the high energy intermediates. And because of those high energy intermediates, a lot of what we see is an anti-addition of the two, of the electrophile and the halogen X. An anti-addition is often seen with polar reactions of alkynes, the two things adding on opposite sides. We'll talk a little bit more about that as we go. Let's start off, though, talking about hydrogenation, wherein we have the metal catalyst and hydrogen gas. We can hydrogenate the alkyne to an alkene. Now, we may have to use a special metal because the alkene that's formed could certainly go on to react with hydrogen gas on a metal like palladium or platinum. So let's look at that reaction. So first we could use just palladium or platinum again on carbon so that we can save a little money, and the surface is all we worry about, and the hydrogen's on that surface, and it can hydrogenate the pi bonds of an alkyne just like we did an alkene. In fact, alkynes are a little more reactive in terms of how much heat they kick off. They are higher energy. So we can have a reaction of these all the way down to an alkane using just the typical palladium, platinum with hydrogen gas. We can have a full reduction. Now I'm showing these as on opposite sides just because typically this will be the favored conformation if we have two alkyl groups off of the alkyne, meaning an internal alkyne. Internal alkyne where the triple bond is not on an end, but these are, let's say, methyl or ethyl groups. But certainly this was a syn addition. We know that the hydrogens come across the same side, but certainly with bond rotation possible, if we go all the way to an alkane, we can lose that information. However, if we have a partial reduction using a Lindlar catalyst is just a polluted form of palladium catalyst, meaning it's less reactive. It typically is made using calcium carbonate as a support. You put palladium with a lead acetate, quinoline mixture, so you have a reduced reactivity of the palladium. So reduced reactivity, it'll selectively reduce the pi bond from an alkyne to an alkene, but not bind well the alkene on the surface. It'll bind these alkynes on the surface of that metal more favorably. But in this case now we can't draw these as being on the opposite sides because there's no bond rotation. So the way it happened, this is still a syn addition. The way it happened is seen within the product because there's no bond rotation. It's evidence that can be still seen as to how this reaction occurred, because you can't just rotate around the carbon-carbon bond here. So they stay on the same side. They came on syn, and they stay on the same side. That's a structural thing. They're cis-oriented to each other in the product. The action occurred in a syn manner to give us a cis orientation of the hydrogens and thus cis orientation of the R groups. Last reaction is a complement to the hydrogen with Lindlar catalyst partial reduction to form a cis product if we have an internal alkyne. If we have an internal alkyne, these being R groups, alkyl groups, we can also use lithium or sodium metal, meaning the reduced form that's very reactive, lithium metal or sodium metal, and ammonia, NH3. If we use those two, we get a metal dissolving reduction, and we can have the hydrogens added on part across the triple bond to make an alkene, but these are now in a trans orientation, locking that in. So just a couple notes on these hydrogenation reactions. Heats of hydrogenation is more exothermic for terminal alkynes, meaning terminal alkynes are more reactive than internal alkynes. Terminal alkynes are more reactive than internal alkynes. So terminal meaning we have a hydrogen on the end of the alkyne. They are more reactive in general, whether it be alkenes or alkynes. Terminal alkynes or terminal alkenes are more reactive than internal. Partial hydrogenation is possible due to the increased reactivity of the alkyne over the alkene. They are at higher energy. The pi electrons a little more active. That's because of some issues in polar reactions regarding the intermediate. Sometimes the higher reactivity is not seen in polar reactions. Lindlar catalyst or lithium with ammonia or sodium with ammonia in any terminal alkyne results in the same product, because certainly if we were to partially reduce a alkyne, you don't know, or you can't tell in the product which of these two is already on and which came on in the reaction, so it doesn't matter with terminal alkynes whether you run the Lindlar reduction, Lindlar catalyzed reduction, Lindlar catalyst, and hydrogenation, or if you run lithium with ammonia, you're going to get the same product if it's a terminal alkyne. Alright, now let's look at the three polar reactions. HBr, we'll look at acid catalyzed hydration, and then we'll look at Br2 across the triple bond. Let's look first just addition of HX to a triple bond. We know this is a strong acid. These are some tags you should make. We know it gives up a proton. We know this then has to attack, and if we have any time a pi bond in an alkene or an alkyne attacking an electrophile, we employ the Markovnikov rule. Put the electrophilic site on the carbon with the most hydrogens. That would be this one. But here's a new thing. Here's a new twist. With alkenes, we didn't have stereoselectivity with HX's adding across a double bond, a alkene. But a triple bond, we choose selectively, or we have a stereoselectivity to anti-addition, meaning the H and the X that are added across the triple bond do come from opposite sides. The idea of this is that the positive charge you would start to form on this carbon as the pi electrons in the triple bond start bonding the proton to the carbon with the most hydrogens. We don't, in most cases, form a true carbocation. It's too unstable. And so at the same time it's starting to form here, a halide is coming in from the opposite side to react with that carbon. So we tend to favor anti-addition. So if this was being attacked and put on the bottom side of the carbon here, then if that proton was being on the bottom side, then the bromine would be on the top side. So they are indeed anti to each other. And they're locked in. We have a history of how things happen. So they came on anti to each other, and that gets locked in by the pi bond. So it tends to stay in a trans orientation. Now if we have excess HX, we can drive the reaction on to make geminal dihalides. Geminal meaning the halides are off the same carbon. Now in general, without regioselectivity, the number of products obtained certainly increases. If we did not have differences in the number of hydrogens for these two carbons, we could have up to 2 products constitutionally, where we have a geminal dihalide with carbon here bonded to two halogens, or if this was again an internal, and we could also bind those two over here. But having a terminal alkyne, we do have selectivity. The proton goes to the carbon with the most hydrogens, while at the same time, almost in one step, we have a bromide coming in anti to that proton that's being bonded to the carbon with the most hydrogens. Now, I'm not going to cover as much detail in terms of the radical reactions, but just like in the case with alkenes, your notes for this reaction are that you have anti-Markovnikov addition of HPR. Again, we have to have terminal alkynes to have that rule employed, but it's still the rule for these reagents in an alkyne. And we have anti and syn addition, so no SS, so there's no stereoselectivity. So with this one here, we can have up to 4 products if we had an internal alkyne. We have a terminal alkyne, so we know at least that we put the hydrogen not on the carbon with the most hydrogens, but we put it on the internal carbon, and the bromine goes here. But they can be anti to each other, or they could be syn to each other. So of course it matters here because the bromine is being locked into orientations to the methyl group that are trans, and here they are cis. So we have 2 products there. All right, moving right along, we do have the ability to add water across the triple bond, just like we did with alkenes. We've seen alkenes react with acid in the presence of water to get addition of H and OH, so H and OH are added. And it's Markovnikov, and it's anti. These will come on, just like in the case of acid with HX. We attack the proton if we're going in this direction with acid and water. We attack the proton while water's coming in from the opposite side. So this proton, let's say, is the one we attach to the carbon with the most hydrogens. The electrophilic site goes to the carbon with the most hydrogens. While at the same time, we can't stabilize a carbocation, we have water coming in from the opposite side, and we've drawn it without the proton here, which could be given back to the solution as our catalytic form of our catalyst in the reaction. Now we have to, because alkynes have higher energy intermediates, sometimes we have to add an additional, I guess, reagent or catalyst for the reaction to occur. So you may see mercuric sulfate added in to help push this reaction along as a catalyst. So we are at a addition product to the alkyne. So we have terminal alkyne, we follow Markovnikov's rule, and we have anti-stereochemistry that we consider. But at this point, this addition product that I've circled does not stop at this point without anything else added. This, what we call enol, will continue to react with itself. It's a tautomerization, so tautology would be arguments where nothing is added to the statement that you've just made. Like saying, I'm a married man and I have a wife. Well, you didn't add anything by saying you have a wife. It was implied that since you're married, you have a wife. You don't need to tell me that. Tautologies are nothing added. We can think of tautomerization as this changing with nothing else added. This proton is going to change positions with nothing else, no other reagent added to this as it forms. This will tautomerize. It'll move. Where does it move? Well, the way to kind of capture where it moves is to draw a resonance form for this structure. The oxygen is a pusher. It donates electron density, some of its lone pair electron density, into the pi bond. So we could draw that by kind of going lone pair to pi, it's a pusher, pi to lone pair. We could say, as we considered that resonance form behind this major resonance form that's neutral, we'd say we have a partially positive oxygen and a partially negative carbon. So the proton just goes to the carbon that's partially negative in that ene all, the ene, carbon double bond, all, hydroxyl group or alcohol. So it goes to this position, and we end up keeping that pi bond that we started to draw by resonance, and we lose that pi bond here that picked up the proton. So this is our keto form within the enol to keto tautomerization. So this is something you must end at. You don't want to end here when you have acid catalyzed hydration of an alkyne. End at the keto, final product. Here we have our hydroboration oxidation reaction. It's a anti-Markovnikov, and it's still syn. We have addition of the boron and one hydrogen across the face of a pi bond, so we would say this would be the one from hydrogen or from borane, and this would be BH2, but we sub that out where it sits and how it sits with the oxidation. We change that BH2 to a hydroxyl group. So these would be the two if we were to look at anti-Markovnikov addition, where the boron ends up, the hydrogen ends up on the carbon with the least hydrogens. This is anti-Markovnikov addition of water. Anti-Markovnikov addition of water. So we would be careful of water. It appears as if it went anti-Markovnikov, so the proton doesn't go to the carbon with the most hydrogens, it goes here. It actually comes from borane, BH3, and then of course that BH2 that was here is switched to hydroxyl group with the oxidation step. But we notice we have an enol, just like we saw up here. What I've circled here is an enol. Now, again, it's the complement to this one because the OH and the H have switched here. The OH, I guess I should say, and the H switch here, and they're on the same side because it's syn. But we can take the enol, and just like we did before, we can take the proton and put it here because this carbon is partially negative. So we end up with the keto form, where in the end our carbonyl is on the end carbon with hydroboration oxidation. Just remember that the CO double bond you're going to from the enol is on the end carbon, and with acid catalyzed hydration it's on the interior carbon. So that's a lot to maybe digest. You may need to watch this again, but these are complements to each other. The hydroboration oxidation, we get what's called an aldehyde, where just so it's not that you need to know that name right now, but just that the CO double bond that you end with is on the end. And this is a ketone, where the CO double bond that you end with is on the interior carbon of that triple bond. All right, two last slides, just quickly. We can take our notes for addition of halogen X, bromine or chlorine. X and X are added. If we use Br2 across the triple bond, these still come on anti to each other, and we can stop at this point because these are electron withdrawing. We can stop at this point, or we can continue on to make the tetrahalide from the dihalide here that we have, the vicinal dihalide, where these are locked into trans orientation. Chlorine or bromine are used for this reaction to make this vicinal dihalide, and again we can go on if we wanted to form the tetrahalide from the alkene. And then last, oxidation. We can oxidize our triple bonds like we did with double bonds, where we completely break the pi and the sigma bonds. And like with alkenes, we put as many oxygens in place of these bonds as possible. So we have two of those bonds from this carbon, cutting the three, going to an oxygen 1 to make a carbonyl, a CO double bond, and then that last one to an OH. So it's again just split the triple bond, pull those carbons apart, and put as many oxygens on as you can to make carboxylic acids. We can do this same reaction with terminal alkynes, but again, these CH bonds are sensitive, that are right off of the double bond or triple bond, and we don't worry about oxidative or reductive conditions. We just have a water workup. And these terminal alkynes give one end from one carbon, CO2, and the other carbon gives us our carboxylic acid. Just need to know those products that are formed. Now we can run the same reaction for either internal or terminal. We can run the same, or get the same product, I should say, by using, in place of ozonolysis with water workup, KMNO4, I guess at higher temperatures, hydroxide and sulfuric acid can also be used to give us these products. Well, that's it. That's our second video on alkynes, looking at what products we can form or what reactions we can have of alkynes. Our next video we'll be looking at dienes. And that will be it. Bye-bye.